Kafka guarantees strict message ordering only within a single partition. If two related events, event A and event B, land on different partitions, their consumption order is non-deterministic, regardless of their production timestamp. To enforce global ordering for a sequence of related events, all those events must be routed to the same partition. This routing decision is determined by the message key and the partitioner implementation on the producer side. The system analyst must define a key that represents the logical boundary of the required ordering. For instance, if ordering is required per user session, the session identifier must be the message key. If ordering is required across all transactions for a specific account, the account identifier must be the key. Any failure to consistently map related keys to the same partition immediately breaks the strict ordering guarantee, forcing complex and often inefficient reordering logic on the consumer. The message key is the primary mechanism for partition assignment. When a key is present, the default partitioner uses a consistent hash function, typically murmur hash 2, applied to the serialized key bytes. The resulting hash value is then mapped modulo the total number of partitions to select the target partition index. This hash function must be stable across all producer instances and language implementations to ensure consistency. If the key is null, the default behavior is round-robin partitioning, which explicitly destroys any ordering guarantee for related messages. Therefore, strict ordering mandates a null-null stable key for every message in the ordered sequence. The key selection must balance the need for ordering granularity against the risk of partition skew. A key that is too broad, like a date, will group too many unrelated events, while a key that is too narrow might not provide sufficient context for ordering.
The standard Kafka partitioner provides adequate distribution for high cardinality keys, assuming the hash function distributes inputs uniformly. However, it offers no control over the specific partition index chosen. If you require specific keys to always land on partition 0, or if you need to route messages based on business logic beyond simple hashing, the default implementation is insufficient. Round-robin partitioning, used when the key is null, cycles through partitions sequentially. While this maximizes throughput distribution, it explicitly prevents strict ordering because related messages produced sequentially will be spread across the entire topic. System analysts must verify that the chosen key space is large enough to utilize all partitions effectively without creating hotspots, a common failure point when relying solely on the default hashing mechanism. When default hashing fails to meet specific routing or ordering requirements, implement the custom partitioner interface. This interface requires two methods, partition and close. The partition method receives the topic name, key bytes, value bytes, and cluster metadata. Within this method, you define the exact logic for partition selection. For example, if a specific set of high-priority keys must be processed immediately, the custom partitioner can route them to a dedicated smaller partition set with higher consumer resources. Ensure the custom logic is deterministic. Given the same key and the same partition count, the output partition index must always be identical. Non-deterministic logic will lead to message reordering and data corruption. Custom partitioners are essential when migrating data or when integrating with legacy systems that impose external constraints on partition assignment.
Strict ordering guarantees established on the producer side are maintained only if the consumer group configuration respects the partition-local ordering. A consumer group can have multiple consumers, but only one consumer instance can read from a single partition at any given time. If you require strict ordering across all messages associated with a specific key, that key must map to a single partition, and that partition must be processed sequentially by one consumer. Scaling the consumer group beyond the number of partitions provides no benefit and wastes resources. Scaling the consumer group to more consumers than partitions will result in idle consumers. If the business logic requires processing related keys in parallel while maintaining internal ordering for each key, the key selection must be granular enough to distribute the workload across partitions, ensuring that related events for key A never land on the same partition as related events for key B. Low key cardinality, where a small number of keys dominate the message volume, results in partition skew and hot partitions. For example, using a tenant identifier as the key in a multi-tenant system where one tenant generates 90% of the traffic will overload a single partition. This bottleneck limits the entire topic's throughput to the capacity of that single partition and its assigned consumer. High key cardinality, where every message has a unique key, defeats the purpose of key-based ordering and increases metadata overhead. Monitor partition lag metrics to identify skew. If skew is detected, the solution involves either rekeying the messages using a composite key that incorporates a secondary identifier, such as tenant ID plus session ID, or implementing a custom partitioner to distribute the high-volume key across multiple partitions using a secondary hash, accepting that ordering is then only guaranteed within the composite key space.
The Sticky Partitioner, introduced in Kafka 2.4, optimizes throughput when the producer is configured for high latency tolerance and batching. Unlike the default partitioner, which hashes every key, the Sticky Partitioner attempts to send multiple records without keys to the same partition until the batch buffer is full or the linger time expires. This reduces the overhead of partition selection for unkeyed messages. Crucially, when a key is present, the Sticky Partitioner still uses the standard hashing mechanism to ensure key-based ordering integrity. The optimization applies primarily to unkeyed messages, grouping them into larger batches for efficiency. System analysts should understand that while this improves overall producer performance, it does not compromise the strict ordering guarantees established by the keying strategy, provided the key is consistently present for ordered sequences. Achieving strict ordering often requires transactional guarantees, ensuring messages are written exactly once and in the correct sequence. Idempotence, enabled by setting Enable Idempotence to true, guarantees that retries do not result in duplicate messages. This is achieved using a producer identifier and a sequence number assigned per partition. The broker rejects messages if the sequence number is not exactly one greater than the last committed sequence number for that producer ID and partition. This mechanism inherently enforces ordering at the producer level, preventing out-of-order writes due to network retries. When using transactions, the producer must explicitly commit the transaction, ensuring that all messages within that transaction batch are atomically visible to consumers, maintaining the sequence integrity established by the partition key.
Log compaction introduces a critical nuance to ordering, specifically concerning deletion events. In a compacted topic, Kafka retains only the latest message value for each key. If a message is produced with a null value, it is treated as a tombstone, signaling deletion. The order in which a consumer sees a sequence of updates and the final tombstone is still strictly maintained within the partition. However, if a consumer starts reading from the beginning of the topic, it will only see the latest state for each key. The system analyst must account for the fact that historical intermediate updates for a key are removed. If the application logic relies on processing every single state transition, log compaction is unsuitable. If the application only requires the final state and the deletion marker, compaction maintains the integrity of the final sequence, ensuring the tombstone is the last record processed for that key. To finalize strict ordering implementation, verify 3 critical configurations. First, ensure the producer configuration AX is set to all, guaranteeing the broker confirms the write before acknowledging success, preventing data loss that could lead to reordering upon recovery. Second, set max in-flight requests per connection to 1. While this reduces throughput, it prevents the producer from sending subsequent batches before receiving confirmation for the previous batch, eliminating the possibility of out-of-order delivery due to network latency or broker failure. Third, implement monitoring for partition lag, specifically on the partitions handling the ordered sequences. High lag indicates a consumer bottleneck, which, while not breaking the order guarantee, delays the processing of sequential events. Regularly audit the key distribution to proactively identify and mitigate partition skew before it impacts service-level objectives.